Thank you. I'd like to thank the organizers for inviting me and for that opportunity to talk among so many people who've actually influenced this work. So I'm trying to get this in my back pocket. Hopefully I'm going to tell you something today that hopefully is interesting. I think it's more interesting than just the aspect I'm going to start talking about, which is financial markets. I think it touches on a lot of the aspects from yesterday, ecology, collective behavior, but it's also, since we're in the physical day today, is that something very physicsy and physical about it that I'll get to in a moment. Just to give you a quick kind of upshot of where I'm heading with this, I'm going to talk to you about something you may or may not have heard about, sub-second trading in financial markets. I'm going to try and convince you that there's something interesting going on. It's not just a faster world down there, it's a new world. And the point is, it's a world that's beyond human response times. And I'm going to try and convince you that there's an interesting kind of phase transition to a new type of behavior, in a new type of world, really, which is really just dominated by algorithms. I'm going to then talk about possible implications for system fragility. One might think, if there's a lot going on in the sub-second world, I don't have to worry about it because I can't access it and nobody else can. But that's not quite the case, as I'll try and show you. And I'll end up talking about something which is really quite speculative, but the results are not speculative, but the interpretation is. And so if anyone has any better ideas than my interpretation of what I'm going to show you at the end, then please let me know. My funding sources are MITRE, ONR, and IARPA, although I'm not talking about IARPA work here. So this is not my work. This is some very interesting, as Doyne said, there are some very interesting works out looking at the networks of financial stability. There's a number of papers out. This is one particular work. It's quite interesting to see, according to what measure you take, as to which banks are connected to which. But of course, what's missing from this type of view is the role of time. And we all know that. We all know that networks involve time. But I'm going to talk about the role of time in finance, which is quite an important one because it touches on actually a physical speed limit. So we all know that nothing can travel faster than the speed of light. On here, I've got the times for return trips for light. So this is light that can go through an optic fiber. Even through an optic fiber, that slows it down. If you were just sending light through a vacuum and then it immediately bouncing back, this is the fastest that it can travel. And just to put up here a kind of reality check on, although these are short times, this is actually quite a long time. For example, London to Chicago. Because all of our laptops, if they're cycling at 3 gigahertz, then in principle, if you could rig up that clock to just do a buy and sell on the cycle of the clock, you'd be able to do 1 million trades in the time that it took just for a trader in London to trade on the Chicago exchange. So if you were sitting in Starbucks at the side of in Chicago, and you had your laptop, you would be able to do 1 million trades. And of course, if you can get in quick, you've got an immediate advantage. So this has set off this whole world, which I really knew nothing about, of the race to zero, as they call it, race to zero latency. And some crazy things are happening. For example, the first transatlantic cable that's been built in 10 years, it's being laid now, not because nice messages are going to be passed between one continent and another. It's purely for traders. And it's purely to shave 5 milliseconds off the round trip. And so they've got cameras following along the seabed looking for the shortest path around the rocks, and just to shave 5 seconds off the round trip. There are chips, I used to work looking at semiconductor processes. But it's quite interesting that there are people building into chips trades. So you build a trading scheme, a trading strategy into the chip just to be faster. And so there's one, the kind of speed record, this was about 6 months ago. Apparently somebody was telling me yesterday it's even quicker now. There are chips around that can process, so they'll take in an input of what the market's doing and spit out a buy or a sell, and also a risk check, apparently, within 740 nanoseconds. Nanosecond is 10 to the minus 9 seconds. But of course, as we know, the human reaction time is, well, mine is certainly a lot longer than a second. But most of us is a lot longer than a second, and particularly if we've actually got to think rather than just have some kind of action. So this is a strange world. And so the extent to which countries are connected, banks are connected, stocks are connected, they're going to be, and they are, 70% of trading is now computer trading on the US market. They're going to be increasingly connected on shorter and shorter timescales. And so time is going to take on not just something that you can just add on afterwards, it sort of is the driving factor. So I want to just, so before moving on, I just want to give, I'm obviously not the first person who thought about fast trading. There's a lot of people thinking about so-called high-frequency trading. I absolutely recommend that you read Doyen Farmer's paper if you're interested in ecological perspective on computer trading. There are a number of people looking at high-frequency trading. However, a lot of it, in fact, I don't know anything that doesn't in this list. They tend to talk about high-frequency trading as trading that's fast. A minute is fast, 30 seconds is fast. And a lot of the crashes that have happened recently, the flash crash of 2010, it was fast, but it was actually quite slow. It was 5 minutes, 10 minutes. So although that's fast, it's very, very slow compared to 10 microseconds or milliseconds, which is the scale on which the trading is actually being done. So I'm going to be talking about things that are much faster than this. So let's just check out, I made a claim about the reaction time, so I need your help with this. I've never tried this out, so I'm not quite sure it works. But I want you to imagine, I don't know if you ever have imagined yourself in a trading, an alternative career in a trading environment, but imagine that you did do that one day and you were sitting in Goldman Sachs, or you go along for their interview, and they're going to check out your reaction. They're going to give you a trading strategy, so I want you all to think you've got a trading strategy. And your trading strategy is, that they've given you, is that you are going to buy when the market goes down. So when you see the market go down, you've got to buy. So you've got a little bit of asset, a little bit of money ready, and you can do this once. It's a one shot. And, I mean, you haven't got any button in front of you, but, maybe you could just kind of clap when you're going to have your one shot, and I'd like to see how this plays out. You're going to see this in real time. So this is how you're sitting looking at a screen. This happens to be American steel, US steel. Sorry, you can't see that very well, but you're going to see stock price in real time. The little colored dots here, this happens to be 1050 on one day in 2010. Little colored dots are the prices you're seeing quoted on different exchanges. So you can buy on any exchange, let's just say that. So you've got to clap your hand when you see the market go down far enough that you're going to buy, and you're going to, then you're going to make your profit. So let's see if I can get this going. I've got an old Mac, so yeah, okay. So this is real time. So as I said, these dots here, I mean, the fact that they're not continuous is, of course, you only get prices when something is actually traded. So you meant to clap, by the way. Oh, somebody already did. Okay, you lost the job. Right? So when the price goes down, we're going to see who makes the highest, the most profit. So carry on. Yeah, you might want to wait a little bit. Oh, you missed it. You missed it. Now, this is what I'm going to talk about today, this thing. Now, this is quite strange. This is something which lasted 100 milliseconds, which is why you didn't see it, or you saw it afterwards, but you couldn't do anything about it. But it's not a one-off. We have gone back in the last few years and found thousands of these. And these are the things that I actually want to talk about, because these as what I'm going to try and convince you, these are the output of this new machine ecology, this new world that's sort of grown up beyond our reach. Okay, so here's the deal with the data. So we trawled back through stock data, all exchanges, across all exchanges, US exchanges, in the past 5 years, around 6 years actually. Around 2006, you don't really see any. Around 2007, they begin to pick up. We've counted, we're only going to count ones, you can change these parameters if you want, but you've got to choose, these are reasonable. If it goes down 10 times, so by the way, this is the thing you just saw. This isn't just some, guy who put his finger down on the wrong button, because then you just see one huge trade. The dots here are the size proportional to the size of the trade. So you're actually seeing the trades escalating down. These are actually traded prices. So there's a real price. People are actually machines are actually trading here, and then this thing is coming back up again. So 10 consecutive downs. It's like 10 throws of heads or tails. Of course, that's unlikely, but not completely unlikely. But we also make the change larger than 0.8%. That's quite large. I mean, that's actually huge on these second time scales. We found about 18,000. There are very, very few of them with a duration of around a second, but there's a huge number with a duration much less than a second. And I'll now show you there are spikes and there are also dips. I'm also going to show you that they're not just simply it's not just simply a faster version of what's going on the daily scale or the hourly scale. This happens to be Bank of America, close to my heart, because I've got my account there. So this is Bank of America. This was coming into 2008, into the Lehman Brothers bankruptcy. You can see down here the price, the price is kind of bobbling around, and I guess people were beginning to pick up that things were going badly. Down here, you've got the volume and the volatility. But up here in purple, you've got every time there's one of these fractures that we all missed, I've put a little thing up here. I call them fracture. I know, just because it seems to me like it's a kind of rip, not in space, but also in time. It's kind of a temporal fracture in the market, in the financial market system. So you could see these things, and they're not really correlated. I mean, to some degree they are, and to some degree they're not. Certainly over here they're not. There's a huge fluctuations in volume over here. I don't get lots of fractures, but I do seem to get this kind of build-up. I'll talk later about the build-up. First of all, I'm just going to talk about the fractures themselves. I'm going to keep calling them fractures. These 18,520. Want to try and understand why are there so many of them, and what are their kind of characteristics? In the lead-up then to the stability, to the 2008 September Lehman Brothers collapse, here are the top, we looked at the top 20 stock. Which are the stock that have the most of these fractures? If you're thinking of something almost like breaking apart, like a kind of aircraft wing, which of these aircraft would you not want to get on? Out of all the stock that, are traded, actually the top 10 are all financial. They're all financial. Morgan Stanley's down here. It has the most fractures. Then Goldman Sachs, Wells Fargo, JP Morgan, et cetera, et cetera, et cetera. Lehman Brothers is in here. And what I've shown here on this bar is, the black up here is read to the right. That's the Standard & Poor's. The cumulative number of red is the spikes and blue is the dips. They kind of track each other. But what happens is they have these kind of onset. It looks quite a way before the actual macro breakage. I'm not going to talk more about this. We're now looking into the kind of breakdown as though it were a kind of cascading failure. I'm not going to talk about that. I just want to show that to you because it's really kind of suggestive of some kind of breakdown. But at the micro scale, at the millisecond scale. So we always tend to think of, that there's nothing down there that can actually affect what's up here in the daily scale. But I'm not convinced. Okay, I'm going to put that on hold, the whole escalation thing. I'm just going to look at the character of these 18,520 fractures. When you do that, when you look at the distribution of them, so I'm going to plot out, just as you would for avalanche sizes. You know, we've heard a lot about the Sampal models. So just as you do on that, so the frequency distribution, a histogram, number of times I get an avalanche of a certain size, so the number of times I get a fracture of a certain size. And I'm going to look at that distribution, and thanks to Mark Newman's work with Aaron Clauset and Cosmo Shalizi, they have a rigorous way of doing the power law testing, which we had to actually augment here because you've got to do the Monte Carlo testing to get the p-value. You don't want to just do that with a few. So we parallelize this the whole Monte Carlo procedure. But what I'm showing here then as the result of that is the best fit power law exponent. This isn't just kind of drawing a straight line. This is following their procedure, which I thoroughly recommend to anyone who talks about power laws. So here's the power law exponent, and here's the goodness of fit. So this is the p-value. And I want you really to focus on the blue line. And here I've got the time scale up here. This is a second. These are the so what I'm going to plot here, I'm going to take, for example, if I take here 1,000 milliseconds, that's 1 second. I'm going to draw out all the fractures that have a duration longer than 1,000 milliseconds, and I'm going to do their distribution, look at their distribution, and I'm going to get the alpha, and that's the left hand, and the p-value, and that's the right side. And then I'll repeat it for 900 milliseconds, and then 800 milliseconds, and I'll go down and down and down. There's a fundamental change in this system as you move between, say, 1,000, so in other words, a second, just above a second, the scale at which we were all operating, down to about 600 milliseconds. There's an interesting asymmetry between those fractures that go down and up and the fractures that go up and down. Why is that? I don't know. But you might think that if humans are going to kind of struggle against machines, if they're going to step in there with their big red button and do something, that they're going to be more likely to do it when they see that this system crashed than when it starts rising. And so you might be seeing here this kind of struggle between humans and machines on this scale and machines down here, and humans are gradually dropping out. I don't know, but that's what it's possible. It's quite interesting to see that actually the fastest time scale that's been recorded of somebody not just kind of putting your foot on the brake, but actually thinking about something and making a decision and then doing something. So a grandmaster in chess, to realize a strategic move, it's 650 milliseconds. Is that a coincidence that it happened to hit there at the 0.1 value, for goodness of it? I don't know. So there's this fundamental phase transition. So therefore, there's two questions. Why are there so many of these spikes? What is it about machines kind of fighting each other that gives spikes? And why is there now this kind of this fundamental change in the distribution of these spikes? It's like another world, another planet where avalanches look different. Here's a model of it. I'm not saying it's the model. It's just a model. And it's a model that quite a few people here in this room have worked on. It's a binary model of a market. Now, binary models of a market have been around for many, back to when Doim was doing it originally, and then we all kind of jumped in, looked at Alpha game and all these kind of things. And everybody always said, binary model, that's not how humans behave. You don't have yes, no, I'll look at some simple binary string strategy. But machines, that's probably quite a good rule for how machines work. So here's a model of what might be going on. I'm going to take a bunch of machines that are not connected together. I'll explain what the connection is in a minute. They're all trying to look at the past record of outcomes, and they're trying to look for a pattern, and they have a couple of internal rules, internal lookup tables, and they'll use the best performing one, and they'll choose that pattern. They'll choose the output of that strategy, and they'll use that. and then they'll go on to the next, they'll update that strategy and they'll move on. It will so happen that if the number of available strategies, or the size of the strategy space, in other words, is small, then by chance, a lot of them will begin to crowd in. They'll collectively use the same strategy, even if it's unwilling, but they'll just do that, if the number of strategies is small compared with the number of machines. Well, we know the number of machines down there in the sub-second scale is large. What about the number of strategies? Well, the number of strategies for a machine is actually, I mean, humans are already out of this now, talking about just if it was just machines. If you've just got machines, then if they're getting data on a timestamp of, say, 100 milliseconds, if you're operating on 200 millisecond timescale, so if you're a trading machine on 200 milliseconds, you've only got the last, you've got the last 200 milliseconds to decide what to do next, if you're doing something every 200 milliseconds. But you're getting data time-stamped every 100 milliseconds, so you've only got 2 bits of data. So you might have a 0-0 if the market goes down, or a 1-1 if the market went up. There aren't that many things that you can do. You can say, well, I've got 0-0 or 0-1 or 1-0 or 1-1. There's only 4 possible patterns that you'd see. And so there's only 2 things you can do, buy or sell. So the actual strategies, if we classify it in terms of things that you can do given a particular history, is actually quite small. And so what we would postulate is that when you get down into this small regime here, you've actually got this crowding, this unintentional crowding in strategy space of the machines. And when you do that, and this is a result from quite a few years ago that we had, when you do that, you generate a price series that has these huge spikes in it and huge dips. They can also recover here. But huge spikes and huge dips, precisely because the machines suddenly begin to see the same, they always see the same pattern, but then they begin to choose the same strategy. They've got 2 rules, and they begin to choose the same one. They all crowd into it. Bingo, they all do the same thing. You've got this huge spike. As you go up in the time scale, of course, you've got more time. The machines have more time to think about things. So they've now got 300 milliseconds, 400 milliseconds, 500. They've got more patterns that they can see. 1, 0, 1, 1, 1, or 0, 0, 0, 1, 1. It's a richer space. It's a bigger space. So the chance of them crowding is less big. And when you get up to 100 seconds, you've also got then humans kind of jumping in, etc. What happens in this model that I just told you about is that you don't just gradually change the regime over. There's a phase transition. There's a phase transition. There's an abrupt change, exactly what we saw in the data. There's an abrupt change. It's not just this gradual change over to machine world. There's an abrupt change. And it happens right around 600 or 700 or 800 milliseconds, right where humans cut out. You can go ahead and get some interesting kind of analytic results. Esteban Moro in this room has done a lot of, he's got a great review on this type of modeling. Interestingly, Dave Cliff in Bristol has just been doing human-machine interaction experiments, and he found something reasonably consistent with this. So in a controlled laboratory experiment, here I've just shown volatility versus this curve, effectively this line of time, and volatility shoots up in this kind of phase transition here. So it's not just price, it's volume. What about the volume? You talked to us about the transaction. Yeah, okay, right. So here's the volume down here. Volume is very different. The volume of the number of trades in this model, at least, undergoes this abrupt transition as well. And if you look at the real data, I didn't show you the volume, but this is silver. I just happened to choose a commodity here. I didn't choose the stock price, but silver here, huge spikes. I mean, is it the same? I don't know. Looks similar. So what we're spending a lot of time now, and I'm not going to go through this, but we're going back to all of that kind of work on these binary games and trying to unravel what it is that makes the situation susceptible to these micro crashes. Why are these micro crashes important? Well, because there's no regulation. The regulation exists for Gaussian markets or near Gaussian markets. All options are written for that, et cetera, et cetera. There's nothing going on at the sub-second scale in terms of regulation. So, that's where we get our funding from through the MITRE, which gets it from the government, is that should there be regulation there? What I'm showing you here, just to show you, is this is the kind of, you can look at the gain move around these states in this de Bruijn graph. When down here, these are the weightings for each of these nodes. When a node begins to get red, it gets hot, it becomes susceptible to trigger a crash. All this to say that there's machinery out there. You know, the effect is new, but the kind of theoretical machinery has been around for about 10 years, so it's kind of interesting. It's a kind of interesting outlet for all those things that we were all doing a while ago. I'm going to go back to this escalation. I've got a couple of minutes left. I'll go back to this escalation. We were kind of intrigued by this. So what is it about this build-up? What happens if I look at the time between the events? So again, a lot of people in this room have looked at bursty time series, looking at kind of bursty, you know, the burstiness of Laszlo and many others, and Luis looked at this. I'm going to look at this now, not overall. I'm going to look at the actual escalation here. It's not much of an escalation, of course, it's stochastic, but you know, you can gradually see there are more and more of these events as you build up here. And what I'm going to do is I'm going to use something which has been around in the marketing literature and psychology literature and actually animal behavior literature for 100 years, animal behavior literature. It's the idea of looking at this in terms of sort of progress curve. That somehow, you know, there's an event, and then something happens, you know, maybe it's due to the system's learned, maybe it hasn't learned, maybe it adapts something, and then there's another event. And those events are getting quicker and quicker. And, and this is a known effect from, as I said, acquisition of skills. You know, this is back to the date 1936. Data was taken on how long it takes someone to sort items, and how, you know, the successive sorting of items, they get better. It happens quicker. Proofreading, et cetera, et cetera. There's also a set of interesting data from Power Law of Practice Journal of Marketing, people looking at internet sites, music sites, how long it takes them to navigate them. You know, they get faster and faster every time they visit. We were interested in this because if you look at this existing literature, there's you know, the people there have looked at how events get faster and faster, and they plot them out according to a power curve, which is exactly the same power curve that Doyne was talking about with Wright's law, but now the cost is in time. They plot this out, and there are two important variables, which is the intercept and the slope. Now, I know, you know, I teach Physics 101, so I know if I give somebody a physics problem, I mean, there are certain students, you give them a physics problem, and it takes them, you know, 5 minutes. And then you give them the same problem, and it takes them 6 minutes. And then it'll take them 3 minutes, and then it'll take them 5 minutes again. Their tau would be around 5 minutes, and their B would be practically 0. And then there are other students, you can give it to them, you know, it takes them 10 minutes to first go. And by the time they're on the second one, they're down to 4 minutes, and then they're down to 2 minutes. And then they've got your job, and then you're out. But the whole point is that there's no set relation. When humans are giving, from what I know, when humans are doing a task, they're against the system, but the system is passive. They've got something they're struggling against, but that system is passive. The problem is passive. All of these problems are passive. Then there's no relationship between the way in which they learn, which is the B, and their initial time. But that's not what we see when we see these struggle problems. I'm going to jump to something completely different. I probably want to some you know, indigenous Indian groups up there. Because we've spent a lot of time in my group looking at struggles, two-sided struggles. And now I'm going to bring it back to what this has to do with the stock market. Here's my attempt at doing mathematical social science, because the equation is just, you know, you add tribes to an insurgency, to a mafia, an army, and then you take away the state, and what does that give you? I've got no idea. But if you look at the look at the events of violent events, these are guerrilla killings of not just indigenous, but also, you know, the mestizo and the, you know, just the general population. You know, since 88 to 2005, they gradually get closer together. Of course, there are all these disruptions, just as there might be, you know, different technology. You know, insurgent guerrillas use different, have different technology. They bring in different technology. The state does something, etc. But you gradually see this same kind of curve. In other words, the time between events initially was large. It becomes smaller and smaller. just over here, just because anyone's worrying about me fitting a straight line through that. The residuals are pretty Gaussian and pretty close to uncorrelated. But we've been doing this in many different systems. And what's intriguing is you get exactly the same kind of behavior. And this is where I've headed to my last point of this kind of generic relationship. I think it's a generic relationship. I'm not quite sure. What I'm plotting here is the B, which is the way in which you learn, you know, the rate in which you learn. It's not a rate because it's a power law, as Doyen was saying, for I do something in an hour, then it takes me 30 minutes, then I do it in 3 minutes, etc. And I'm plotting that against that first time interval. So, for example, I just showed you an area in Magdalena in Colombia where the guerrilla and the FARC and the ELN, that's that point there. And there was a certain B, which was the slope, and there was a certain tau 1, which was the initial value between attacks. And then I've got all these other values for all those other departments, municipalities in Colombia. And they follow this line. Now, they shouldn't do that because, as I showed you before, if it's humans against some kind of task that doesn't change, there ain't no line. It's not there. There's no line. And the same here. There's no definite dependence between tau 1 and B. But when there's a struggle, when there's some kind of struggle, and the state hasn't changed here really, when there's a struggle, the guerrilla are struggling against the state to inflict injury, it induces this kind of correlation. But we don't just see it for the insurgency. This brings me back then to the market. If I take the time, if I do the same exercise for all of those different stock, the top 10 financial stock, and I look at the relationship between the time between the first two fractures and the rate at which the fractures appear, again, they seem to follow this same line. And I think that's because the machine or the algorithm is fighting against the system. And of course, the market will always react back, as Doyen was saying. There's a market impact. It reacts back on what you do, unlike the one-person tasks. We've extended it in other areas. We've looked at protests, same thing. These were protests in cities in Poland leading up to pretty much up to the breakup of the USSR. And we have a group, we collaborate with a psychology group in Miami that look at mother-infant. You wouldn't think mother and infant. I'm sure father and infant will be even worse, but mother and infant interaction. Apparently, the infant just wants smiles from the mother, and the mother just wants smiles from the infant, but of course they're not actually compatible. And so the infant cries. And so they have there's this huge area in psychology looking at baby reactions. And the reason is you want to try and detect which babies might have autism and there might be abnormal reaction. And it would be great if you could recognize that from this type of test. But again, these dots are like individual municipalities or individual stock or individual cities with protests. They each have their own B and their own tau value, but they seem to follow a similar line, which suggests there's something kind of innate or generic underlying them. I'm going to leave you with the last slide, which is my kind of attempt at a theory of that, but it's not really very good. It gets you the fact that B should be around, has values in the range of 0 to about 1.5. And I like it because it's a kind of physics thing, but it doesn't really get you the explanation of why these follow this nice straight line. It's the idea of, we all know the Red Queen theory. You run on the Red Queen runs on the spot because everybody else is running. But now I want you to think of the distance that the Red Queen is from everybody else. So everybody else is the other system, like the rest of the market, or the mother, or the government in Colombia, or the state police in Poland. So the Red Queen, who's the algorithm or the guerrilla insurgency, is running, and maybe occasionally they get ahead. Now the Red Queen theory has nothing in it about getting ahead. So if you imagine the Red Queen's lead is some kind of stochastic walk, then you'd think that her advantage, the relative advantage, would go up as the number of steps, the number of successes, to some power which is not 1. It's to some, it would be 0.5 if it were a random walk. Since the advantage of the red queen is going to be something like 1 over the time between successful attacks, the more advantage I've got, the quicker I can make attacks. You might expect then that the result will be that the time between successful events for one side, the red queen, against the opponent, and therefore in dyad struggles in general, would go like this power law. But as for why they follow the particular line, that coupling, I haven't quite got yet. So I'll just leave you with that. Thank you very much, and open to any questions.